Welcome to our Organic Chemistry 2 test review. Some people will be coming in either in person or online as we go through this, but that's okay. We'll just kind of keep going from where we are. If you have your microphone on, I would ask that you go ahead and mute it unless you have headphones. At least unless you need to ask me a question. Totally okay to stop me and ask me a question at any point. So please feel free to stop me and ask me a question at any point if you have any questions. All right. For now, let's go ahead and begin. Even though I do have this practice test up, I want to actually start by opening this up to any questions you may have before we begin. Not necessarily even on this test, but like anything from the daily assignments that Dr. Gilchrist hands out, or anything from, the book or your homework or whatever. I am willing to answer any questions on that you think would be helpful. Or should we just go ahead and dive into the test? And you can answer via chat, or you can turn your mic on and let me know.
I know I personally have way too many questions to even put them together for you at the moment.
Okay. So, sorry, there's some sort of a weird random drill. Our campus got closed down yesterday because of craziness and school shooting. But we are back. All right. Well, let's go ahead then and just dive into the practice test. And then if anybody has anything that they want to go ahead and bring up at any point, just let me know. All right, so for the first question, it says, draw the organic product formed when the following alkene is treated with H2 and palladium with carbon. That draw all possible stereoisomers as products as well. So here's the thing. With this catalytic hydrogenation, you have to keep in mind that the hydrogen is either going to add, this is an overhead view here. This is an overhead view. The hydrogen is either going to plant itself right on top, or it's going to come in from the bottom. Now let's go ahead and assume that the two hydrogens, plant themselves on top of this double bond that we're looking at from above. If they do, it's going to push this bond down, and this bond down, and this bond down. Okay. Now, for the purposes of what we're trying to do with the stereochemistry here, we can think of it as all of those going down, but then you could go ahead and tilt it so that it's really just going down in one way rather than in all three ways. So I can tilt this forward so that when I have the hydrogen plant itself on top of there, that the only bond going down is this one. Now, just for the sake of clarity, I'm going to go ahead and number these a little bit. And sometimes you'll find actually one of the most useful things that you can do in OChem is go ahead and number your carbons when you're doing things like this. So I'm going to just go ahead and number this. This will be carbon number 1, 2, 3, 4, 5, and 6. I'm drawing with the mouse, so it's not perfect, so I apologize. Actually, you know what? I'm going to go into my mouse settings and slow this bad boy down. And then I should be able to draw maybe a little bit better, but we'll see how that works. Okay. So now it's important to recognize, okay, so here's your number 1 carbon, okay? This used to be a double bond. Now it's a single bond because the hydrogen dropped on it. The hydrogen's also going to drop on this carbon here. And that's, once again, it's going to push these two down. But once again, I can tilt, and it's going to push all three of them down, but I can tilt this such that one of them remains in the plane and one of them remains down. Okay, so if I tilt it back a little bit, like in other words, so that this CH3 group starts going back into the page, that means that I'm going to actually have a second dash. I know this is really weird. You usually don't have to see a dash on a dash like this, but in this case, there's no other way to really draw this effectively. At least not that I know of. So then you also have this coming down here. But because I tilted the CH3 back, that means this CH2, CH3 is going to be in the plane. Okay? CH3 in the plane. Now, the other thing that you're going to get is, there we go. You're going to get a wedge. The wedge is the hydrogen that came out, right? There's a wedge here. The hydrogen planted itself on top. And then you're also going to get another wedge here. Because remember, you have two hydrogens. They both plant themselves on top here, pushing the groups below them down. So this dash right here is in reference to the wedge here. So it's going down, and then on this one here, with this carbon here, the CH3 is pushed down, and so you got hydrogens coming up in both cases. Okay. Now, admittedly, you don't actually have to show, or you don't have to indicate specifically the RS configuration, but you could. You could here. So let's go ahead then and draw the rest of the molecule. The rest of the molecule would consist in this CH3 coming out as a wedge. And technically speaking, in a bond line structure like this, you wouldn't really need to write the CH3. But since the professor did, we'll do as well. Notice that this one is not affected at all by the hydrogen, because hydrogen is only adding to the double bond and pushing those things down, pushing those groups down. Now, that is one possible stereoisomer, and notice it says draw all possible stereoisomers. So I'm going to go ahead and highlight that here. Draw all possible stereoisomers as products. So there's another stereoisomer that we need to draw here, and that would look similar to this other one, except the hydrogen would actually be coming in from the bottom. So that would actually pop this out, pop everything else up. So here I have the hydrogen coming in from the bottom now, here. And then I have the wedge. I can't draw. It is hard to draw. It's hard to draw on a mouse. Anyway, so there's the wedge. That's, here's your number one. Let me change my color real quick. Here's my orange. There we go. Here's my number one carbon. And then, of course, don't really necessarily need the number in this case, actually, but oh well. So then the carbon group is the one that's wedged up. But then I also have another, because the hydrogens came from the bottom, that means this CH3 group, which has popped down before, is actually popped up here. And then you have the CH2, CH3 coming out here. And then, of course, once again, the hydrogen it's in the back. Both hydrogens are in the back because they both came in from underneath. Does that make sense? I realize those are a little bit messy drawings. I apologize for that. Can zoom in. That makes things a little bit easier. I don't know. Does that help though? Does that make sense? Any questions on that? And I am monitoring the chat as well. It's like I can also hear you. So if you want to type your questions in the chat versus speaking, you can totally do that. So we good? Ready for the next one?
Did something happen to the CH3 at carbon 2?
Oh, no, my bad. I'm sorry. Good point. I just forgot to draw it. It's still there. It's still there. That hasn't changed with either one of them. My bad. Thank you for mentioning that. I wasn't paying close enough attention. I apologize. Any other questions? All right. I will go ahead and move to the next question then. And by the way, if you want to skip ahead to other questions, please let me know. I'm more than happy to do that. All right, let's take a look at question number 2. So draw the organic products of the following reaction, including stereochemistry. So in this case, the first thing to recognize is that you have to be familiar with some of these reagents, specifically MCPBA. That's metachloroperoxybenzoic acid. Whenever you have a peroxy acid and an alkene, you should be thinking epoxide. So the first part of this product is going to be this. You're going to get this cyclohexane with, instead of a double bond attached to it, you're going to have epoxide. And I've drawn this both as wedge, and you can draw it as dash if you want, because the truth is you will actually get both. And technically speaking, it really doesn't matter, because the truth of the matter is that this is actually, neither one of these are chiral centers. Neither one of these two carbons here or here, neither one is a chiral center. One on the right has 2 hydrogens. The one on the left has a line of symmetry going right across the middle of it. Okay, so since neither one of these is a chiral center, we don't have to worry about stereochemistry so much, even though it says including stereochemistry. Now, where is the OH going to attack? Is the OH going to attack on, I'll call it carbon A or carbon B? So I do want this to be active session as far as possible. Yeah, please feel free to.
Carbon A?
Carbon A. All right, and why do you say that?
Because it's closest to the ring.
Okay. Now there
Is
is
it
a
because it's more
condition under
substituted?
there is a condition under which you would actually have something attack carbon A, but in this case, carbon A is more sterically hindered. Well, and carbon A is more sterically hindered. Now, the only way that you would go ahead and attack carbon A instead of carbon B is if you had acid catalyzed conditions. Because, for example, if this was H3O plus for the second step instead of OH minus, then you'd get the protonation of the oxygen, and then you'd get this, you'd effectively get a partial carbocation in this position here, which would make it attractive to the to any nucleophile that would come in, like water. However, in this case, in base or even neutral conditions, you're not going to get it adding to the more highly substituted position. And the reason is because of steric hindrance. It's just going to be more sterically hindered. It's going to be a lot easier. It's going to be a lot easier for the OH minus to come in and add on the other side here. So this OH minus is actually going to come, and it's going to come and attack here. And that's going to kick this up here. Now, you don't have to draw the mechanism, but I'm showing this because I find that knowing the mechanism is one of the most valuable things that you can do to really master organic chemistry and have a good sense of it. Otherwise, you find you're just memorizing a bunch of stuff that doesn't seem terribly related. But you start to see the universal patterns once you start looking at the mechanisms. Okay, so the OH comes in here, followed up with H2O, which means you're going to protonate this guy. And so, well, the first thing that's going to happen is that you're going to get this. You're going to get this O minus. It doesn't have a hydrogen. Okay. And then you're also going to get this OH that just attacked. Now, here's the thing. Do I really need these two? Or let me ask you, do I need those wedges, that wedge and dash? Is there any chirality here? What do you think?
No. You
No.
have two carbons connected to other carbons.
Yeah, exactly. You actually have a plane of symmetry here. So the plane of symmetry is basically using the highlighter. I'll just use a highlighter. It's like right down the middle here. Oh, come on. Come on. Oh, it doesn't want to let me highlight. That's lame. Okay. Fine, I'll just draw it with a yellow. You got your plane of symmetry right here. So yeah, it doesn't really matter. So you don't really have to worry about stereochemistry. All water is going to do is going to protonate that O. It's going to become an O minus. So your final answer is actually going to look something like this. It's going to be this. Do, 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 do. And yes, you do have to listen to me sing. Just kidding. I'll keep it to a minimum, I promise. Okay, there you go. And that would be your final product. Make sense?
Do we have another carbon at the end of that wedge, or at the end of the dashed wedge?
With the dash, there is a carbon there. I'll go ahead and mark it in gray just for clarity. All right, here, yeah, there is a carbon here. Just like there's a carbon here. That's why there's a bend or a kink in the thing, because there is a carbon there. Because that carbon is basically carbon B. If you look at the original label, I put A or B.
Oh, okay, I see it. You're right.
Yeah. All right, cool. All right. Any questions over that? Or we'll jump to 3. Okay. Moving on. Now, if there's any you want to skip ahead to, please let me know. There is a good chance that we're not going to be able to finish this whole thing by the time by the time our time is up. So feel free to let me know if you want to skip ahead. All right, number 3. It says draw a stepwise mechanism for the reduction of this epoxide with lithium aluminum deuteride. The reagent is like lithium aluminum hydride, except the hydrogen is replaced with deuterium. And then it says, okay, so this is really not too complicated of a mechanism. But the key thing here to recognize is that you have this lithium aluminum deuteride, which is basically like lithium aluminum hydride. So I have a D. It's basically 4 negatively charged deuteriums, or hydrogen isotopes, attached to aluminum. And so what this enables is the deuterium to act like a nucleophile effectively, because it's so small that it wouldn't be able to effectively act as a nucleophile without a little bit of help. So this kind of stabilizes it. And essentially, these electrons, I'm going to change the color here. I'm going to use, oh, I'll use that color. These electrons are going to come in, and they're going to attack which position? Because lithium aluminum hydride, is it basic or is it acidic? What do you think? Is this basic or acidic condition? Yeah, very basic. H minus is an extremely strong base. So this is going to come in, and it's going to attack which position? Is it going to attack A or B? What do you think?
A.
Yeah, it's going to attack A. A is the less highly substituted side. So one of these pairs of electrons here is going to come and attack A, but it's going to attack from the opposite side because it's going to be kind of like an SN2 attack, right? So it's going to attack from the opposite side, and it's going to kick these electrons out to this oxygen. Now, if it attacks from the opposite side of this, then that means we're going to end up with the deuterium atom being what? Is it going to be like a wedge or a dash?
A wedge.
Yep. And the OH, and the oxygen, the O minus, is that going to be a wedge or a dash?
It'll remain a dash, won't it?
Yep, it'll remain a dash because it's basically just being kicked out and over. But it's still locked in position because it's still going to be in the same relative position. So I got the dash oxygen, and I have a deuterium. And unfortunately, my D's and my O's look kind of similar because I'm terrible at this. But basically, I have this O minus here, 3 lone pairs, and a negative charge. Now, the only other step here is the step for part 2. I mean, this is actually a concerted step mechanism, except for the fact that I also have to do a little protonation. This is actually a pretty easy mechanism to draw. So in that case, all I have to do is protonate this with the water that comes in step 2. The water will also neutralize your lithium aluminum hydride. Welcome, in-person student. Thank you for coming. Oh, no, I said 3. Sorry. That's okay. Don't worry, I recorded the rest of it. Okay. All right, so here's the deal. And actually, I just have to make sure nobody else is waiting in the wings to kind of get in. Okay, good. All right. So yeah, at this point, all you're going to do is you're going to protonate. Let's see. Use my other color. Protonate this oxygen. Whoop. Yeah. And there's your mechanism. And you get your final answer. Any questions on that? That was pretty straightforward. I told you I couldn't promise you there would not be more singing. So. There we go. Ah, well, what am I doing? That I already grabbed the hydrogen. See? One of the most important skills you can have as a chemist is an attention to detail. So, don't forget that. Don't be like me and make silly mistakes. Okay. Next, number 4. I don't see any questions with this, so I'm going to go to number 4. Cool? All right. Your lack of disagreement means consent. All right. Next, it says draw the organic product of the following reaction. This is pretty simple. You have a primary alcohol. So you just have to recognize this is just reagent memorization. PCC is a mild oxidizing reagent. So this is just going to oxidize to a aldehyde. That's right, an aldehyde, not to a carboxylic acid. Next, says draw the organic product of the following reaction, including stereochemistry. Let me ask you this. Is there any stereochemistry to the product of number 5? What do you think?
Doesn't Lindlar's catalyst make it a cis molecule?
Maybe. I want to know if it makes this a cis molecule. Is this going to make it a cis molecule in this case? So it is
No, because
cis.
it's not symmetric.
What'd you say?
I would say no because it's not symmetric.
Well, the key thing here is that there's already a hydrogen here. So if I add a hydrogen to both here and here, even if I do draw this like this, it is syn addition in that they both add on the same side. But because I'm adding a hydrogen, it already has one hydrogen there. Remember, you only have stereochemistry with organic compounds if each double bonded carbon is bonded to 2 different groups. So this double bonded carbon here is already bonded to 2 of the same groups. So it doesn't matter, because it's a planar molecule, it doesn't matter what's on the other side, even if they're different. This is not going to be a cis. This is not going to be a cis molecule. This would actually have no stereochemistry whatsoever. If you flip it, it's the same thing. So no stereochemistry. So you could just draw it like this. Sometimes the Professor Gilchrist likes to throw this including stereochemistry stuff, and there's no actual stereochemistry to show. This just goes to prove that Dr. Gilchrist is evil. No, I'm just kidding. I love Dr.
The only reason there's not stereochemistry is because the carbon on the left-hand side has 2 of the same group. If it were to have 2 different groups, then it would matter, correct? Like if it had...
then it would be cis. So, like for example, if this thing over here is a CH3 instead of an H, then yes, you would have stereochemistry. It would be cis. Exactly.
Okay, thank you.
Yeah, no problem. Next, this is what are the products of the following reaction? So what does ozone do? How well have you memorized your reagents? What does ozone do to double bonds?
Doesn't it add an oxygen on both sides?
Yeah, well, specifically, it cuts the double bonds in half, right? Ozone cuts double bonds. It cuts them right in half. It actually cuts triple bonds too. But in the case of triple bonds, you end up maxing out the number of carbon-oxygen bonds, and you get carboxylic acid and junk if you have a triple bond. However, with double bonds, that is not so. You only get a double bond O replacing the double bond to C. So you cut those, you cut those bonds in half, and anywhere there was a double bond is now going to be, you're going to have an oxygen attached to it with a double bond. So one of the things I like to do with this is number my carbons. I'm actually going to start here. I'm going to start from the break. You don't want to cross the break. In other words, you don't want to enable this 1, 2, because those 2 carbons, 1 and 2, are not going to be connected. Okay. So in this case, we're not numbering for the purpose of naming the original compound. We're numbering for the purpose of finding out what the new compound will be. So I'm going to actually start numbering here. I'm going to number away from the break. 1, 2, 3, 4, 5, and then I'm going to keep going over here, 6. Okay. So I see I have a 6 carbon chain, but then I also have this 1 carbon that's all cut out by itself. So this gives me a 6 carbon chain and then a 1 carbon group that's all out by itself. And so that's going to give me 2 products here. The first product, 1, 2, 3, 4, 5, 6. And I'm actually going to go ahead and number my carbons just for clarity. 1, 2, 3, 4, 5, and 6. Now here's the thing. carbon number 1 had a double bond, right? So now carbon number 1 has a double bond O. But this is going to be an aldehyde because you only get the carbonyl. You don't get anything else. The hydrogen that was there before, it's still there. It's just going to be a double bond O. Now 2 doesn't have anything, 3 doesn't have anything, 4 doesn't have anything, but 5 does. 5 has a double bond. So I'm going to draw another double bond O on 5. And then I look at 6. Well, 6 also has a double bond. So I'm going to put a double bond O on 6 as well. And there is a hydrogen also coming off of that was on there before. It was on there before. And it's still on there now. It's just that that double bond C was replaced with a double bond O. Now the other thing that's going to be formed is a C double bond O, because it's just a 1 carbon group. Once again, that 1 carbon group over here, it had 2 hydrogens before, and it still has 2 hydrogens afterwards. The only difference with it now is that you end up getting a double bond O, so now it's like formaldehyde. Does that make sense? Any questions on that? What's the second reagent do? Basically, what you have to understand here is that there's kind of like this intermediate complex. What really happens here is that you got this, you actually get this 3 oxygen complex. Like this, okay? It's not terribly stable, but you get this 3 oxygen ozone complex. And then this also had a 3 oxygen ozone complex. That's what the reaction with ozone does. Ozone plants itself on top of the double bonds like this. But the dimethyl sulfide basically splits those. Basically there's a little kind of chain reaction here where it's a little bit complicated to go into, but essentially as far as the mechanism, and I don't think you're not really expected to know it, but essentially this bond breaks, the double bonds form there, and then this oxygen ends up getting taken off by, I think, the sulfur or whatever. But the dimethyl sulfoxide just finishes the work, shall we say, of splitting the bonds. All right. Any other questions on this one? We good? All right. Let's go ahead and jump to number 7. Like I said, we can skip ahead at any time. Just let me know. Now, number 7 says, show what steps would accomplish the following synthesis. And you may use any necessary organic or inorganic reagents that you would like to use. In this case, I mean, there's a couple of different things you could do here. But truthfully speaking, the easiest thing I think to do would be to recognize that, you know, how would I get, you can do like backwards design. How could I get this? How could I get a carboxylic acid? Well, one of the things you learned in the alcohol chapter is the role of strong oxidizing agents, right? So you could get a carboxylic acid from CH3, CH2, CH2, CH2. Pardon me, sloppy writing. I know it's kind of atrocious. All right, and alcohol. So you have basically I have 4-carbon alcohol or 4-carbon carboxylic acid here, I could get that from a 4-carbon alcohol. All I'd have to do is add chromic acid, or like commonly chromic acid is not something that you don't store chromic acid. It's just far too unstable. So whenever you use chromic acid, it's also kind of toxic. You usually make it what's known as in situ. What that means is that you make it as you need it by pouring in reagents that will create chromic acid when you put them in solution. So commonly, like you'll see sodium dichromate with H2SO4. And then in addition, you'll also see water. So water, sodium dichromate, and H2SO4. This will produce chromic acid. You might also see CrO3 with H2SO4 and water, and that will also get you chromic acid. Or sometimes they get lazy and they'll just write chromic acid H2CrO4. But effectively, that will give you the conversion from this alcohol to this carboxylic acid. Now the question is, can I go from this to this? Is that possible?
I have a quick question.
Yes.
Oh,
there
we go.
Go ahead.
Chromic acid. Could we also just put Jones reagent, or do we have to write out the chromic acid?
I mean, I think you could put Jones reagent. I think part of that depends on how strict your professor is, but your professor is going to know what Jones reagent is. You could put Jones reagent if you want. Technically speaking, it's more letters, but, you know, more power to you.
Well, I have my skill crest, so I was just curious.
Oh, for sure. No problem. Yeah. Yeah, I think that would be fine. I don't see any issue with that. So then let me ask you, what could you do, or could you do? Is there a reaction, is there a reagent that would directly convert that 1-butene to 1-butanol? What do you think?
Yes.
So one of our students said, could you use H2SO4 dilute? And that's not correct. You can't do that because H2SO4 dilute would give you an alcohol, but it would give you the more highly substituted 2-butanol. Could you get 1-butanol? You were going to answer. I'm sorry, I didn't mean to interrupt you. Go ahead.
Yeah, so you're gonna use the BH3TTF, whatever. I don't remember exactly.
Yeah, no. You're right. You're right on the money. So it's BH3. So this is going to be a hydroboration oxidation, a BH3 and a THF. Absolutely, that is 100% correct. And then you can follow that up. You have to follow it up with the second part of it, which is sodium hydroxide or just hydroxide and H2O2, hydrogen peroxide. That hydroboration oxidation will get you the primary alcohol. So that's all you have to do. So like the original reactant was this, and then that turns into this. Somebody wanted it to be a skeletal formula. What would that look like? And it would look like this. So 1-butene goes to 1-butanol, which then gets converted into butyric acid or butanoic acid. Bam. Rock on. We did it.
I'm sorry, I have another question.
No questions. No, I'm just kidding. Go ahead.
Oh. For the BH3THF, what are the requirements for that again? Like what are like the best cases to use it?
Okay, so I mean, strictly speaking, anytime you have a double bond, you could use BH3THF, but there's no reason to use BH3THF unless you want a less highly substituted alcohol. Like in other words, if the double bond is in a position where one side is more highly substituted and the other one is less highly substituted. And what I mean by that is, whenever you have a double bond, there is potentially 4 carbon groups that could be attached to it, right? So you could have, well, a double bond. Each carbon could have 2 additional carbon groups. So you could have R1, R2, R3, etc., and R4. Now, if, let's say I'm looking at the carbon on the right here, this carbon, which I'll draw in blue, although it might not be blue because I'm colorblind, but so essentially that carbon is attached to 3 other well, it depends on what R1 is. Let's say R1 happens to be a CH3, okay? But let's say that R2 happens to be a hydrogen, okay? Let's say it's just a hydrogen. Well, that carbon then, that carbon here it's attached to 2 other carbons. It's attached to the one on the left, I'll mark here, and it's attached to the CH3. Now, let's say on the other side, you had a CH3 over here that was attached to that, and then you had a CH3CH2 attached over for R4. That was your R4, a 2 carbon group. Well, see, this carbon on the left here, this one, which I'm actually going to color it a different color, that one actually is attached to 3 carbons. So the more highly substituted means that it is attached to more carbons. And so the one on the left is more highly substituted. So in this case, there's a difference between the levels of substitution between the 2 carbons. If I want the less highly substituted one, the one on the right, to get the OH, then I would have to use hydroboration oxidation. If I wanted the one on the left to get the OH, I would have to not use hydroboration oxidation. I could use a couple of different things. I could react it with hydroxide. Well, no, not hydroxide. Hydroxide wouldn't work. But you probably would use acid catalyzed hydration. So basically like dilute H2SO4, as our other student mentioned. Or you could potentially also use oxymercuration, demercuration. The difference between oxymercuration, demercuration, and acid, and let me put the reagents down for that, but like oxymercuration, demercuration involves the use of mercury acetate. So that, and in H2SO4, concentrated H2SO4, I think. And then you follow that up with, that would be like the first reaction, and then follow that up with like a water, I think. And that would give you your more highly substituted alcohol addition, OH addition. Now, the difference between that and the other possibility, which is easier to write, the other possibility, you can either write it as H3O plus, or you can write it as H2SO4, but you would have to write it as dilute H2SO4. So you'd have to actually include the word dilute. Otherwise, you could write it as H3O plus. Because it doesn't have to be H2SO4. It could actually be phosphoric acid, H3PO4, but you'd want a dilute acid. Now, the difference between those two is the dilute acid allows for rearrangement. So if you have a more highly substituted carbon, then when the carbocation forms, because both, basically the H2SO4, the dilute H2SO4 involves the carbocation mechanism, and anytime you have a carbocation form, you can have rearrangement to a more stable carbocation. Oxymercuration, demercuration prevents rearrangement because it, instead of having a carbocation mechanism, it forms a mercury acetate complex that kind of like sits on top of the double bond, or where the double bond was, and then the water comes in later and attacks, and then the mercury gets removed. So the mercury one prevents rearrangement, but the acid catalyzed hydration does not. So it just depends upon the molecule which one you'd want to use. In the case of this molecule over here, the one I just circled. If I look at, if I wanted to put it on the more highly substituted, the darker blue, darker purple, whatever it was, that if I wanted to put it here, basically, I'd have to look at the other carbons around it. Well, this carbon is tertiary in that it has 3 carbons attached to it. The carbon over here, well, this is a primary, and this one down here, the CH2, that's a secondary. It's only attached to 2 carbons. So a tertiary carbocation is going to be the most stable carbocation, and therefore, there's going to be no rearrangement here. That carbocation will stay there until the water comes in and puts the OH group on it. So with that one, I could use dilute H2SO4, no problem. But if you were to have, say, a different molecule, let's say you had something like this, where you had a double bond here, okay? And let's say you wanted to get this. So I want the OH to add to the more highly substituted side, the more highly substituted side in this case being this one. I could not use acid catalyzed dehydration because if I did, what would happen is that the carbocation would move to this position, which is going to be more stable because that's a tertiary carbon, whereas the original one is a secondary. So for this one, I would have to use the oxymercuration demercuration to get this product. I know that's a really long answer to your question, but does that help? Does that answer your question?
Yes.
Okay, cool. I know there's a ton of reagents from Organic Chemistry 1 that you kind of got to dredge up in your mind. You didn't think you'd ever have to use that again, did you? All right. So now let's go ahead and jump into 8. Now, I'm actually not sure what your professor really means by this particular problem, because this is from one of her practice tests, or one of her tests she actually gave. It says, devise the synthesis of 1-pentanol using acetylene as the only organic starting material. But then she says, you may use any needed organic or inorganic reagents. Well, if I can use any organic or inorganic reagents, does that mean that I can just do this? I mean, there's a couple different things you could do. So I could say, well, number 1, I have acetylene, which is a triple bond. I know I need 1-pentanol. 1-pentanol is going to be this thing, an OH attached on the first carbon. Acetylene only has 2 carbons, whereas 1-pentanol has 5. So I have to add 3 carbons to this. And there's a couple different ways I could do this. One is I could go ahead and I could start with sodium amide, which is NaNH2, and that would rip off one of those terminal hydrogens, and I could follow it up with I could follow it up with I don't know, something like, oh yeah, a 3-carbon group. CH3, CH2, CH2, Br. And what this would do is you would have your acetylene group, acetylide group, act as a nucleophile. It would come in and it would kick out the bromine, and you'd end up with this molecule. 1, 2, 3, and then 4, 5, triple bond there. Okay. So then what do you do with this thing? Well, once you have this thing, I keep in mind I want the OH group on the first carbon. There's a couple of different things that I could do with that. I mean, I could first reduce this with Lindgler palladium and turn that into a double bond, and then use sodium borohydride. So So I'll actually show both mechanistic pathways. So I could use, well, what I originally thought of was this. You could use hydroboration oxidation of an alkyne, which is basically use R2Br, basically a substituted boring group, R2BH rather. And this could be like disamyl borane or 9-BBN, something like that. And then typically you put it in with like diglyme or something like that, but I'll put diglyme right here. This is similar thing. Maybe you might be able to use THF, I'm not sure, but I'm going to put diglyme. And then for 2, then you do the same thing you did with your hydroboration oxidation. It's OH minus and H2O2. And if you do that, 1, 2, 3, you're going to get essentially the OH is going to add to, this is going to get converted into an alkene. The OH is going to add to this, but here's the problem. This is not a stable molecule, so it is going to almost immediately tautomerize, and it's going to turn into, from an enol into a aldehyde. And then once you have the aldehyde, then you can go ahead and you can reduce it with either lithium, with lithium aluminum hydride probably, LiAlH4. And that gives you 1, 2, 3, 4, 5 oxygens and a OH. Okay? Cool. Now, alternatively, sorry, go ahead.
I don't understand how you went from a single bond to the O to a double bond to the O.
You're talking about the tautomerization, going from the double bond with the OH to a double bond O?
Yes.
Okay, so tautomerization, this is something that was covered last semester, but I'll show you how it works. Basically, if you're looking at this double bond, okay, so we got our O and you got our H here. And okay, so it's this kind of internal reaction that occurs. It's a little weird, but basically the double bond electrons come and they grab this hydrogen here. And actually, I think it actually starts out with this. What happens is the oxygen donates its electron here. That kicks those double bond electrons out and that grabs the hydrogen. And then the electrons connecting hydrogen to oxygen break off and stick on oxygen. So you end up with a double bond on oxygen and this carbon here getting that extra hydrogen. And that's called tautomerization. And that turns the enol into this.
Okay, thank you.
And does that help?
Yeah, I'm just going to assume it just happens.
for clarity's sake, I'm going to actually change the color of this. This orange hydrogen. This is not shown. It's actually this one. So that orange hydrogen is that orange hydrogen. And so yeah. And let's see. Let's make a fun color. I'll put gray. I know that's not fun. I lied. But let's say this is a gray hydrogen here. Over here, that gray hydrogen is going to have attached to this side. And there's still another hydrogen. There was a second hydrogen that was here to begin with. It's there. Now this has 2 hydrogens, the one that was originally there and the one that it grabbed. Does that make sense? A little bit more?
Yes.
Okay, cool. All right, so yeah, so that's one way to do it. The other way, if you like it, just to kind of show you what all your options are, because it is kind of important to know the different pathways. So you could also have Lindler, basically a poisoned catalyst, Lindler palladium and hydrogen, and I would just turn this into an alkene, and then you could also just go ahead and convert that to, you could use hydroboration oxidation, a slightly different form that we used above, which is just BH3 and BH3 and THF, and then the same bottom reagents would work, the OH and the H2O2. And the OH minus. Alternatively, there is another way to do this using acetylene as the only organic reagent, period. But I don't think, because she says you need organic or inorganic reagents, I don't think she expects you to do that. That would take a lot longer. And just to maximize the effectiveness of our time, I think I'll skip that one. But yeah, doing it this way, you'd get the same 1-pentanol that you would doing it the other way. So whichever is easier for you. Okay. Any other questions, or are we good with that one? Any other questions on that one? Or does that make sense? Are we good with that? Okay, cool. All right, next one just deals with a little bit of resonance. Just to recall to you some rules of resonance that you may or may not have forgotten. When you're trying to figure out what all possible resonance structures are, it's a good idea to keep in mind that you only want to go from atom to bond or bond to atom with regards to electron movement, because the resonance structures show electron movement. And like, for example, I would not jump these electrons all the way over here and have them be a lone pair right there. Okay, so I'm not going to do that. Instead, what I'm going to go ahead and do is have them go from atom to bond. So these electrons will go from atom to bond. But this, unfortunately, because there already is two hydrogen, there's one hydrogen, I lied. Sorry, there's a double bond. There already is one hydrogen here. This carbon already has 4 bonds. That when this when the electrons follow the yellow line or whatever color line that is, and they form that double bond right there, you're going to actually have this double bond have to break, but those electrons are going to go from bond to adjacent atom. So bond to adjacent atom, I guess it's orange. They're going to bond to adjacent atom. They're not going to go bond to bond, they're going to go bond to atom. So you're not going to put them as a new double bond here. You don't want to do that. That'd be skipping it. All right. So then I have an equilibrium situation. It's going back and forth here. Or rather, this is just a multiple resonance structures. So I have 1, 2, 3, 4, 5. I have my double bond oxygen. I have 2 lone pairs on that oxygen. And I now have a lone pair here with a negative charge here. Okay. And I have a double bond here. Okay. So then the next thing I'm going to do is move these electrons again. Once again, bond, or atom, in this case, atom to bond. But that's going to put too many electron groups on this carbon. It'll be 5 pairs of electrons or 10 electrons. You can't have that. It's octet rule. So this is going to have to come up here and go on the oxygen. And so then I'm going to go ahead and get, sorry, my final resonance structure. I only have to draw 2 more. So now this has an oxygen here. 1, 2, 3, 4, 5, 6, minus double bond here, double bond here. And those are my resonance structures. Cool? I'm going to assume that makes sense if you don't ask me questions. Okay. Skipping to number 10. Says rank the following compounds in order of increasing stability. Increasing stability. Well, okay. So in this case, you're looking for the double bonds that are conjugated, okay? And what does it mean to be conjugated? It means to have the same hybridization across multiple atoms. So I'm going to take this color, which I think is red, and I'm going to say that this is your sp3 hybridized carbons. And I'm going to take this color, which I think might be blue, but I don't know. And I'm going to say this is your sp2. I still see color, I just don't see it the same way you do. So I can't tell if things are like blue or purple or whatever. I know it's weird. All right, so with this one, with the blue one, I'll go ahead and do this one. So this double bond means that I have 3 electron domains, and therefore this is going to be sp2 hybridized. I say 3 electron domains because you have to remember there's also unshown hydrogens, right? So that's 3 electron domains. This one is also going to be 3 electron domains and sp2 hybridized. So is this one. So is this one. So is this one. So is this one. So how many sp2 hybridized atoms do I have in a row? I also got this as an sp2 hybridized atom in this one. In this first compound, how many sp2 hybridized atoms do I have in a row?
6.
Yeah, 6. Now, unfortunately, these sp3 hybridized atoms block delocalization. So as long as all the atoms are sp2 hybridized, the pi electrons, the double bond electrons, can freely move across that entire region however they want. But when you have a sp3 hybridized atom in the middle of it, that blocks the movement of electrons. So they can't move around past each other anymore. So I have 6 sp2 hybridized atoms in a row. What about the next one? For this one, how many sp2 hybridized atoms? You say 8? Yeah. There's 8 sp2 hybridized atoms in a row for the next one. And that means that the more sp2 hybridized atoms you have in a row, the more conjugated it is, and therefore the more stable it is. More conjugated means more stable. So these are all in a row. That's 8. So this would be, and then we look at the last one. How many sp2 hybridized atoms are in a row in this one at any point?
Just 2.
Just 2. These are all isolated single bonds. These are all isolated single bonds. So this has literally like no conjugation at all. So as a result, this one here with the most double bonded, the most sp2 hybridized atoms in a row, this is going to be the most stable. And the one on the bottom is going to be the least stable. Stable. Yeah, okay. The way, I'm sorry. Oh, okay. Well, okay, so if you're looking at an individual isolated double bond, then yes, the more carbons attached to it, the more stable it is. But if you're looking at whether or not conjugation is going to affect stability more than the number of alkyl groups, because conjugation actually allows for real delocalization of those electrons. So having two double bonds, all like double, single, double, where you have 4 sp2 hybridized atoms in a row, that's going to provide vastly more stability than, say, having a tetrasubstituted alkene, where you have 4 carbon groups attached to a double bond. But you're right individually in that within the context of just a single double bond, yes, the more carbon groups, the more stable it is. Yeah, conjugation is more important, and that's specifically what this question is asking about. All right, so then let's take a look at this one. It says, now this is one that kind of throws some students off sometimes, but it says 2-methyl-1,3-cyclohexadiene is treated with 1 equivalent of HCl. There are 2 major products. One product predominates at high temperature, the other at low temperature. Now, technically speaking, this is not correct. There are actually 4 major products. 2 that at high temperature, 2 at low temperature. But you'll see what I mean. They're basically stereoisomers. And I think that the professor was just like not caring about stereoisomers at that point. Okay, so what is the mechanism for this reaction? So whenever you're looking at a diene like this, whenever you're looking at a diene and you have like an HCl adding to it, you're gonna want to look at see which is going to give you the most stable, carbocation. So of these positions, which I'm going to go ahead and label here, where do you want the hydrogen to add so that you would get the most stable carbocation? So you want the hydrogen to add to A, Seth? Yeah, that's correct. Now there's actually 2 possibilities. I mean, in one possibility is that you could have the hydrogen add to C, or you could have the hydrogen add to D. If you had the hydrogen add to D, you'd get a carbocation here, right? And that would allow for resonance delocalization of the carbocation. The other, more likely and more important position would be for hydrogen to add on A. Because if hydrogen adds on A, I started drawing A, I'm going to change it to an H, sorry. If hydrogen adds on A, that means your carbocation is this one, a tertiary carbocation, which is the most stable carbocation you can have. Actually, an allylic tertiary is really the most stable you can have. Because an allylic carbocation is actually, it adds an extra level of stability. So, okay, so here's the deal. This is not going to be the best because it doesn't give you the most stable carbocation. If you have this come down here, this bottom one, then essentially what's going to happen is that this is going to be double bond, and you're going to get a positive charge here. But basically the positive charge, the carbocation, is going to be between 2 secondary positions. Whereas on the top case, you actually have resonance that allows for this to become and you actually get both of these, this to become this carbocation here. This is a hydrogen. That was the hydrogen, the initial hydrogen that we added. There's the double bond here, and now you have your positive charge here. Now, I'm going to go ahead and erase the bottom one because this, like I said, this bottom carbocation, it may form a little bit, but it's really not going to be it's not going to be any significant amount of product. This is going to be your significant product between one of these two. And how does that happen? Well, essentially, you have HCl here, and the electrons on from the double bond come and attack the hydrogen, and then the electrons between hydrogen and chlorine leave with chlorine, and the hydrogen ends up adding to, and I don't like that, it looks like too much like an N. I'm going to redraw that. But basically, this hydrogen is now here. So the chlorine then can attack either one of these two positions. I have chlorine here that I got from above. It has 4 lone pairs and a negative charge. Okay. So basically, this chlorine is going to come and attack here, or this chlorine is going to come. Oops. This chlorine is going to come and why is it not working? Okay. It's going to come and attack here. And so if it attacks the first carbocation, the tertiary one, you get this product. Now here's actually you get these products, because that chlorine can either attack from the top or the bottom, and the two sides of this molecule are not identical. So that's why I say you actually get 4 major products. So here's your one product, and then you could also get this one. Because this, like I said, this is going to be a chiral center. You have Cl up. You can either attack from top or bottom, in which case it's going to give you 2 different isomers. 1s, 1r. The double bond is still here. Okay, so those are the 2 you get from this one. And the 2 you get from the other one are going to be well, the chlorine is, once again, it's going to either attack from top or bottom. You get a chlorine here. I'm not going to bother drawing the lone pairs. It's too much work. And you could also get this one. Forgive me, I know my drawing is terrible. Okay. So basically those would be your 2 products you get from there. Now, notice the position here. And I'm actually, just for the purposes of pointing this out, I want to distinguish between 1,2 and 1,4 addition. So you have your original hydrogen that added here, right? And here you have your original hydrogen that added here. Notice since the hydrogen and the chlorine added right next to each other on the two molecules on the left, that's called 1,2 addition, because they're right next to each other, 1,2 addition. And the other one, it's 1,4 addition. Think of this hydrogen being the 1 position. You know, you're 1, 2, 3, 4. So 1,4 addition there. Now here's the deal. What is potentially unstable about the first molecule? Or why would, let me put it this way. Why would the second molecule, or why would the second group of molecules, these guys, be more stable than these guys?
Is it a steric
more
issue?
substituted?
So, sorry. Let me have. Reagan, go ahead. You say first. Or were you not talking? I don't know. Or, yeah, go ahead.
That wasn't me.
Oh, sorry. Amanda?
Is it a steric hindrance issue?
A steric hindrance? It's actually not steric hindrance. It actually goes to one of the things that we talked about earlier with the stability of a double bond.
Like the second set of like the like the two molecule on the right side is have more substituted conservation.
Yeah, this is a more substituted alkene. You have, this is a tri-substituted alkene. Oh, whoops, sorry, I didn't mean to mark that one. But I'll erase that. But it's a tri-substituted alkene. There's 3 alkyl groups attached to that double bond. Whereas on the other, and the same thing with this one, 3 attached to the double bond. Where on the other side, this is actually only di-substituted. Okay? And because that chlorine is on a tertiary carbon, this is actually a very reversible reaction. So if you look up here at the carbocations, which one of them is the more stable carbocation? The one on the left or the one on the right? The left, yeah, exactly. Because it's a tertiary. So this carbocation, the one on the left, forms more easily, it forms more quickly because it's lower energy. It's a lower energy intermediate. But the product is less stable. So if there's a sufficient amount of heat, that will reverse that. That chlorine will leave, go back out. The carbocation will rearrange to the other side. And then when the chlorine comes and attacks this is the more stable product here. And so this is what the more stable product is referred to as what type of product? Thermodynamic, that's right. So this is the thermodynamic product. I'll just write thermo because I'm lazy, and because it's hard to write on this. Thermodynamic product. Now, in the other one, because it forms more quickly because of the more stable intermediate, this is called the kinetic product. It forms more quickly. If you want, just out of curiosity, if you wanted the kinetic product, what conditions would you have? High temperature or low temperature? Low temperature, exactly. And then the thermal would be a higher temperature. All right, cool. Are we good with this? Any questions? All right. Let's go ahead and kick into Diels-Alder. A little bit of time to do this. So Diels-Alder, these are kind of a little bit tricky, but this is what diene and dienophile are needed to prepare the following compounds. One thing to remember is when you're talking about dienes and dienophiles, this is a Diels-Alder reaction, obviously, and the product of a Diels-Alder reaction is always the formation of a new ring, 6-membered ring with 1 double bond in it. Occasionally you'll have 2 double bonds, but that would mean that you have a triple bond that you're reacting with the diene. So first thing I want to do is I want to look for, and the bonds that are the formed bonds in a Diels-Alder reaction are these ones here. Because basically, whenever I have this, that means that the double bonds used to be here and here. The new double bond tells you the double bonds used to be on the other 2 sides of it. And those formed bonds are the ones that I marked in red and in the blue object here. So looking at this dienophile, I would actually cut here, or looking at this product molecule, I'd actually cut here and here. Because the only 6-membered ring present is the 6-membered ring formed with these molecules, or with these atoms, carbon, 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 carbon. So I cut at those two positions. Those are the two formed bonds. And if I do that, I need to recognize that so I have a 5-carbon ring here. I have a 5-carbon ring here on this side. That's what I originally had, a 5-carbon ring. And so it looked something like this. I also have to recognize that the double bond, which is shown initially down here, that's not where it was originally. That's where it got put after things got moved. This used to be a diene. So the double bonds should actually be here and here. And I'm sorry? And there's two chlorines attached. So as just kind of a, let me see, just kind of a note, this carbon here is this carbon here. And so there's two chlorines attached to that carbon. It's the same group, so there's no stereochemistry. You don't have to worry about wedges and dashes. And that's one of your reactants. The other reactant is going to be the rest of this. The rest of this. And there should be a double bond that was the dienophile, double or triple bond that was the dienophile. In this case, that means that double bond should have been right there. So the next molecule is going to be that 5-membered ring that has that oxygen in the middle here and the 2 double bond O's out here. There's a special name for that compound. I can't remember what it is offhand. But it's like conjugated. So there you go. Those are going to be your 2 reagents for this one. So take a second to do this next one. I want you to try to do this on your own. I'll give you a minute or so to cut this apart and come up with the 2 reagents. And after a minute or so, I'll go ahead and show you the answer. All right, let's take a look. So this should be 1,3-butadiene, because essentially what you're doing is you're going to be cutting these 2 bonds here. And in addition to 1,3-butadiene, you would also get this dienophile. You could also draw the double bond O going out the other way. It doesn't matter. But yeah, there you go. And that's essentially what you would get. This is a cis. This is a. You notice these are both up. These 2 positions are both up, which means that This would have to be cis, not trans. Now, skipping ahead to 13, it says draw the products of the following Diels-Alder reaction, including stereochemistry. Now, this is tricky, and this is where some students kind of get messed up. And because we don't have a whole lot of time, I think I might just go ahead and go over this one with y'all. But basically, your dienophile is going to be these two carbons here. And then your diene is going to consist of focusing on these here, although the entire molecule is the diene. And just for the sake of clarity, I am going to number this to these carbons, 4, 5, and 6. Okay. And I'm also going to show you these electrons are going to come and they're going to form a bond with this carbon here. And these these electrons are then going to come and they're going to form a bond with number 4 here. And that's going to give you a 6-membered ring, but the thing is we also have carbons 5 and 6 attached to that as well. So this is actually going to be a bicyclo compound. And the product is going to look a little bit weird. It's going to be kind of like this. And this is how I draw bicyclic compounds, so you can draw it differently if it's easier for you, but okay. Okay. So essentially my bridgehead carbons are going to be carbons 1 and 4. I'm actually going to go ahead and label these now so you can see them. 1, 2, 3, 4. But 5 is actually up here. 5 and 6 got pushed up out of the way. And I'm going to call this A and B. A and B. And A and B are actually over here. Okay? So I'm just going to go ahead and erase, A and B or whatever. Now the truth is this could actually come and, you could flip this so that A is on top and B is on bottom, and that would change the orientation. That's why you get 2 stereochemical products. And basically, generally speaking, if it was a cis thing, it would tend to be endo, which means that both of these groups, when I say these, I refer to these, both of these groups would be going down. But because this is trans to begin with, that means one's going to be going down and the other one's going to be going up. So I actually essentially have 2 situations. I got one going down, one going up. And let me see this. Change the color. Yeah. Okay. So essentially I'm going to have this C double bond O single bond OCH3 up here. And then I'll also have a C double bond O single bond OCH3 in the down position here. So one's going to be up, the other one's going to be down relative to each other. And then the other isomer is just going to be the opposite. The other isomer is just going to be the opposite. You're going to end up having, I'm going to have Oh, whoops, let me erase that. I don't like it. Okay. So then I'd also have, in this one, I'd have the double bond O, single bond OCH3 here in the down position. And then with this one, the C double bond O, OCH3 would be in the up position. I'm not saying I'm not terribly great at drawing these things, so but I hope you get the idea. Does that make sense? And of course, there's also another hydrogen that was attached to the opposite position. Here's a hydrogen here and a hydrogen here. And you will get both those products. Any questions? Okay. Ooh, it looks like we're out of time. And unfortunately, I want to stop the recording so I have time to upload it to YouTube and send it out to everybody. But I'll tell you what. I will scan the answer key that I'll scan the answer key that I made here of the last problem, and you can check it out. I'll send it out to you along with the video of this recording. Deal?
Thank you so much.
Deal.
Yeah, you're welcome. You're welcome. Thank you for coming. All right. Well, I wish you the best on your test next week, and I hope you guys knock it out of the park.
So do we.
All right. Take care.